Ladies and gentlemen, this is the axisymmetric jet setup that we will be using to calibrate a pressure transducer. So we've got an axisymmetric jet that's fed by an air system. You can see the air line is moving in from the left-hand side of the screen, and we've got a breadboard set up to capture the rest of the data, and you can see some other things on the desk where I have a camera set up, etc. So we've got the axisymmetric jet itself, which exhausts air being fed in from an airline. So that's coming around. We've got a mass flow rate and a pressure meter, and there's a tap that controls the flow in and out of the entire system. So that's the pressure regulator and the pressure meter, flow meter, and the regulator on the left-hand side. So the tap is actually sufficient to control the flow rate for this experiment, because we just need to have a variation in the amount of air that's going over this jet, and we can also control the flow. We can control the pressure into the jet, into the pedostatic, using the vertical position, which I'm demonstrating here, and the longitudinal position as well. So we're only using the total pressure for this jet because an axisymmetric jet into the atmosphere has the same static pressure as the atmosphere. So in the original experiment that accompanied this laboratory, you would be given a calibration for the pressure transducer and then use this setup to actually create some data for the flow that's occurring in this axisymmetric exhaust jet. So a more worthy exercise is actually for you guys to perform the calibration yourself. As discussed in class, we've got a pedostatic probe, the static port of which is left open. We're not actually using it because the static pressure in the jet will be the same as the atmospheric pressure. We've got the total pressure, which is ducted off. So this is the total head and then duplexed into a Y. And then we have with some really fine work there on the zip ties, we've got one pressure tube going into the total or gauge pressure of a PX138 pressure transducer. And I'll supply a wiring diagram for this one. And then we've got the other pressure tube where it's split up in the Y going into a manometer, aka the manometer. So you'll note that it's graduated in inches and in decimal inches, and the case to the right is where you'll see the camera that will actually be looking at the manometer during the setup. Looking at the PX138, the power supply is supplied by the breadboard. The device itself can accept an input voltage from 8 up to 16 volts, with the output being scaled proportionally because it is a ratiometric device, as we discussed in class. Now, I noticed when I was supplying this with the quoted 8-volt excitation, because there's not particularly large pressure difference being provided by this jet, the output was incredibly small. So I chose to increase the excitation voltage to around about 16 volts or just below. This meant that I was effectively doubling the output and making the device twice as sensitive and giving me twice the precision in my results. But unfortunately, the input voltage the maximum input voltage that we can record using the analog to digital converter is 10 volts. So we were unable to record the excitation voltage of 16 volts, and I had to think, well, how can we cope with this? And then I thought, well, we had something we developed previously in the laboratories, which is the humble voltage divider. So those are I believe, 200 ohm resistors. It didn't really matter what their value was as long as they were exactly the same. So using two identical resistors, we're able to halve the voltage that's being recorded. So there's a 16 volt excitation or thereabouts, and it is recorded as an 8-volt excitation. So it's 15.5. We actually record around about 7 and 3. We'll just take a closer look at the pressure transducer itself now. So we've got a PX138. This is the 0.3 psi variant. There are 4 terminals on this device, and if you Google the PX138, you'll be able to find the actual diagram and what all of those terminals confer to. 1 is excitation, 2 is common or ground, 3 is the signal out, and then 4 actually doesn't do anything, and those are from the bottom to the top of the page as we've got them imaged. Please excuse my disgusting thumb. So the way that we're powering this is the lowermost cable on here is pin 1, the so the brown is pin 1, green is pin 2, black is pin 3. So brown is the excitation, then we've got green is then connected to the ground, or it's actually connected to the negative voltage here, it's not connected to ground, and then the topmost one is connected to the signal out. So we've got the input voltage being supplied by the positive and negative terminals, which is what's being supplied to these two vertical rails, and then those are measured using a voltage divider, so we can actually get an output signal that is of a value that is then recordable without reaching the threshold of that upper limit. If we were to supply a 16 volt input to the ADC, it would simply just record it as 10 volts due to that thresholding. So data is being recorded using the MATLAB NI data acquisition system. I'm going to record the computer screen separately using screen recording on the computer, and I'll try and sync all those videos together so we can see what's going on. It's not in this horrible wavy format, but I've written a MATLAB script that both takes the data, plots the preliminary data on the screen, and then records it with a file name that you can select. So I will share this this M file with you guys so you can have a look at it, use it in the future if you wish to, and if we get a chance to go into the laboratories, then you have something that helps you understand how data is taken using a data acquisition system. It took me a while to remember how to use MATLAB again. I kept finding myself putting index 0 for index 1. That's just part of the problem with switching between systems, switching from Python to MATLAB. But let's see if do I run it. So I'm running now, I'm taking 5 seconds of data, and what it's going to demonstrate is the average gain. So it asks you for a file input name. If you don't supply with a file input name, it just deletes the data, and what we're showing in those 3 graphs is the excitation, the output, and then the gain. And I can see that what I've remembered to do in this piece of code is to double the excitation voltage, so it reads the actual value rather than the value that's being recorded. So that's why there's nothing being displayed in the top plot, because actually I set the y-axis to be 0 to 10 volts. So I think when I did this in the code, I took a little bit long. When I did it in the video, it took me longer to figure this out than I wished it would. But let's see if I can figure it out. This was only this morning. Here we go. Do I figure it out? Let's check. So I'm showing what this data. So that's the data. The first row is the excitation. The second row is the output. So we've got about 15 volts excitation, about 6 volts output, and presenting those versus time. So here we go. I've realized that it's to do with the vertical axis. Changing that, running this, then it will record 5 seconds of data and then plot it. So we see we've got excitation, output, and then I've got the output divided by the inputs. And then it takes those data and saves them as a comma-separated value file.
The first thing we need to do in an experiment like this is test whether our transducer is working. So the first thing is first I've gone through the data sheet of the transducer, and I can see that's it. And you can download this, you go find it online. See if it says that we need to have an output 0, when it's a 0 excitation of about 3.5 volts. And I know that these have an output voltage of about 4 volts, which is close enough to tell me that these are working. So the next step I want to do, I want to actually run this setup. I want to run it at a low, medium, and a high output. And then I'm going to check whether there's a linear response in the transducer. I'm not particularly caring about producing accurate, precise data. I just want to check whether there's a linear response. So I'm going to record a low, medium, high check. And then we're going to see if data is receiving the data. Put the camera onto the manometer, so you guys can see it move, and then we will record the stuff and get the data.
Right guys, so we're going to start taking some data for this laboratory. Doing this on my own is kind of a bit of a pain, so hopefully I'll be able to sync all these videos together. The first thing that we're going to do is, as I said, was take a 0, a medium, and a high set of data, and I want to then use the information from the manometer, which hopefully you can see on screen, to just check whether we've got a linear response from our transducer. So I'm going to take my 0 first. I don't need my ear defenders on because I'm not running anything on the jet. So if I run this, it's now going to start recording some data. Okay, and these data are going to be my check 0. That's my check 0 data. You're going to have I'm not going to be able to really narrate this very well when the jet's on, so I'll try and maybe do some narration after the fact when I spend hours mixing these videos together. I've got to sync up all the audio from like 3 videos, and that's going to be a bloody pain. But that's my check 0 that we've got now. I'm now going to put my ear defenders on, and I'm going to take a high reading off of the both transducer and the manometer. So let's just see what we get. So while that last data file's just saving, I took 4 data files there. I've got the 0, high, I did a medium, and then a low. So what we're just going to check to see that I wrote down the approximate delta H in decimal inches that we've got from those data and what we should see from the camera. Now when we're actually performing the full calibration, I expect you to have a more precise measurement of those. Take those images and do what you can by checking out the actual data for each of those. And sorry, get a slightly more precise than the sort of ballpark estimate I've just taken with each of these. So what you can see is we've got a check 0, check high, check medium, and a check low. And then each of these data files is a big, large text file. So we've got the time, inputs or the excitation, and then the outputs here. So there is no gain in this data file. There's only the 2-day files. You've got to take the output and divide it by the inputs. But what I've done in each of these is I've recorded the average gain. I must have divided it by, yeah, I've rounded it to the fourth decimal place and multiplied it by 1,000. So these are, I thought that it would get rid of the decimal place, but it hasn't here. I should have divided it by 10,000. Doesn't matter. So I can now just plot these data and I can just see if I've got a linear trend. So I'm going to try and remember how to use MATLAB. Let's do I'm going to just go through these in increasing order. So I've got 0. I'm just going to plot the delta H versus the approximate gain. Obviously, for the actual calibration, you guys are plotting the delta P, but since delta H is linearly proportional to delta H, I can just plot those, and this will then show me whether I've got linearity in my transducer or not. So 0, 0.4, 1.2, and 2, and those data correspond to the gains of 456.6, 470.9, 495.5, and 518.5. And let's plot these with crosses and a line through it. See if I can remember how to use MATLAB. Oh, that looks pretty linear to me. Okay, obviously I'm not including any error bars on this. We're not doing the full calibration yet. This is just checking whether I've got a response from my transducer. We could have done this using an oscilloscope. I just choose to do it using the actual setup that we're going to be using, because this is then testing every part of this measurement system, from the actual output, checking the pitot is working, and getting the data all the way, checking that the manometer is working, and then also further checking that the excitation is working, checking that my transducer is working, checking that the ADC is working. So the whole setup is working, and that's a really important thing to understand with calibration, is that you should always endeavour to use the exact same setup that you'll use for the actual calibration as you would be using for the real experiment. So what I'm going to do now is I'm going to record some more data. I'm not going to write anything on these data files. I'm not going to write the approximate H. I'm just going to give them numerals, sort of 1, 2, 3, 4, 5, and then you guys are going to correspond those to the actual data, the actual information you've got from the manometer. So you guys can then get those delta H's from the manometer and tie them up to those data files. So let's start recording some. I'll record maybe 10, and then I'm going to ensure that I've got a few doubles. So I'm going to take successive measurements at the same valve on the axisymmetric jet, which means they should be at the same pressure. And this just is another way that we can check the repeatability of our data points. So I'm going to put these back on. Like I say, I'll record maybe 10 data files, and we'll see what we get out of this. I'm going to call these all like Cali something, okay? Cali 1, Cali 2, Cali 3, just so that these data files are then distinguishable. So first things first, I'm going to take a calibration 0. Don't really need these on yet. What I was trying to show you with my watch before it came off, it showed that it was 100 decibels. So these are important. So Cali 0. Cali 0, what's that? Iowa 6. Okay, so I've got my 0. It's recording those data. I'm not going to, even though those data have been grabbed and they're just being written in a CSV file, I could start the jet while it's saving, but just in the interest of making sure nothing's disturbed, I will wait. I'm now going to record these. What I'm going to do is I'm going to put the jet to as high as I can. I'm going to then move the jet locate. I'm going to remove the pitot-static location and see if I can get a higher pressure measurement. So I'm going to get my highest I possibly can. Right, so we have a bunch of different data files taken now across the range of the experiment. You'll see that I started to go down in delta H, and then I took one repeat that was higher up. It's different means that you can load different transducers. Sometimes you want to load a transducer in the direction you'll be loading it in an experiment. Sometimes you want to do it randomly, sometimes you want to do it linearly. For this experiment, it doesn't really matter. What's important now is that I do another check at the end. So I took a 0 at the start, I'm going to take a 0 now at the end. So at the beginning, I took a calibration 0 and had an average gain of 456.6. So I'm going to call this Cali 0 end. And thankfully, we're within one decimal place. So actually, this is within to the 4th decimal place because I've multiplied these by 1,000. I should have multiplied these by 10,000 really. But we can see there's no change in our transducer over the life of the experiment. There's a very small change effectively. So that's important to check when you're doing any sort of experiment, is that you are keeping an eye on what your data are doing. And that's why I had it work out the average gain and print it, append it to the end of the file name. So these data files now are available for you guys. The video of this experiment is where you should get the delta H from, and the delta H is what you can use in conjunction with, bear with me 1 second, I'll just grab the bottle. Okay, with the dry manometer fluid that has a specific gravity as listed here, 0.826, which is not the same as its density. Okay, so we're going to go through how we do the actual calibration in a data reduction video, but I'm not going to tell you how to do all of it, okay? Because I've already given you guys a good Jupyter notebook that goes through how we produce a calibration graph. The bulk of what you have to do is get the corresponding delta H's off of this video. So 30 minutes sitting there, watching down, pausing, trying to get them as precisely as possible from the instrumentation that we've got. I suspect that if you pause it and inspect the video, you might be good down to 0.05 of an inch on here, maybe. I just kept showing my phone during this to show you that I was observing this, which is the image from the camera, and not just fanning around on my phone. I wanted to just show you guys that. So, these have been recorded on separate devices, so I'm going to need to spend a bit of time messing around with getting the video to work. I hope it makes sense, and I hope that you guys have enjoyed seeing this laboratory. It's a shame that you guys could not get in here to do it. We're going to do something very similar for the next one as well, recording all of the steps and recording sort of my narration of the whole data reduction through the whole data acquisition, so you guys can understand it. So, have fun guys, and I'll see you later.